Hi, Andrew McLaren here. We're going to be going over isotopes, atomic mass, and their percent abundance. These are really common problems that you'll see in chemistry trying to help you show that you understand like atomic mass units. Um, but conceptually, they can be kind of weird for people. So I want to take a minute to look at the math and think about what's going on with the math and why it's working out that way with the averages, and then really talk about like what is an isotope conceptually, and then actually do some of these problems. So we'll get to them, but we're gonna work on understanding them first. Okay. So I first wanted to start by helping you understand the average calculation part of this problem. So we're not going to talk about isotopes for like the next couple minutes. Um, Basically, when you have an average, you can take the certain values that you have, like m1 is some value, and then multiplying that by like the portion or fraction of the total sample set that you have there. And if you add those all up, you get the average. This is typically just kind of like given as a formula and not really explained. So I wanted to take some time to do that. But you can see this in effect. Right here, I have some different heights and their portions. So this is like 12 times zero point 0.5, 13 times 0.25, and 14 times 0.25. And you can see in this situation, the average is, it's a little bit more than 12, but it's pretty close to 12, which kind of makes sense given how most of our sample was 12. You can see if I tweak the values like over here, uh, when more of the portion is 14s, like if like you have more heights that are like close to 14, your average is going to be closer to 14. Same thing here. I just kind of played around with the values. I made it so that it was mostly 12 and a good amount of 14, and then it's kind of split between the two, so the average comes out in the middle. And then here it's almost exclusively 12, and the average is pretty much 12. And so that's the type of stuff that you typically see with these types of problems, is like some sort of portions where it's like, oh, it's mostly this one number, so our average comes out close to that. But I want to help you also explain this by thinking about average problems in general. So if you think about like a lab where you measure the height of some plant, maybe there's 100 plants, and so you can say 50 of them are 12 inches tall, 25 or 13 inches tall, and 25 or 14 inches tall. You could write this out like that. You've probably done some average problems where you add up like 10 different numbers and then divide by 10, right? And you get the average. You can do the same thing here. You can write out 50 12s. I've just done dot, dot, dot just to save some space. And then I could have 25 13s written out. And then I could 25 14s written out. And then we have 100 numbers written out. So we divide by 100 and we'd get the average. I believe if I did that calculation, I would get this number, the 12.25 or 12.75. You can also rearrange this a little bit. So you can, instead of writing out that repeated addition, you can say, well, I've got 50 12s. I'm just going to take 12 times 50 and then add that to the 13 times 25 and the 14 times 25. And then we can also rearrange that again slightly. Because we have 100 in the denominator, we can write this out as three different fractions. Like we could have 12 times 50 over 100 plus 13 times 25 over 100. But you can rewrite that like this is basically the 12 times, and then you've got this fraction right here. And in that case, you can say that it's a portion. So the average calculation that you're used to seeing has just been rearranged. So now we've got our part and our whole here, and then this is what the value is of that part. It's just slightly different. It's rearranged, but we can generalize the average formula into something where essentially you have like these like Normally it's the sum of heights, which you add them all up divided by the number of plants, but you can also look at it as the portion times the height of that portion and adding those all up. That's like the big picture on the concept behind the average part. Before we do the calculations, we need to talk about what an isotope is. An isotope basically is a different version of an element. Like carbon has a number of different versions. You've probably heard of like carbon dating or carbon 14 or carbon 12. People oftentimes have heard about those particular isotopes before. So we're going to start referring to that. So you might see it written like this, where you've got the element and then you've got two numbers with that element. The larger of the two numbers is going to be the protons and neutrons added together. So you can kind of see like right here, this carbon atom, there's 6 protons and neutrons in the center in the nucleus, and then 6 electrons around the outside. So the top number is the protons and the neutrons. It's how much it really weighs. And then this bottom number is the protons. And you don't really need to give that number if you've already said what the name of the element is, because as you can see, carbon always has 6 protons. So just be careful. Whenever you see an element, sometimes it's written with the larger number up there, and sometimes it's also written with it down below. The larger number just has to do with the protons and the neutrons, because they both have mass. You need to keep both of them in account when we're talking about how heavy something is. Electrons do have mass, they're just super, super small in comparison. So we don't really care about them. So the smaller number basically tells you, okay, this is the element. And then the larger number tells you like, okay, well, how many neutrons do you have with that proton? That's the main idea with an isotope. And you can see like carbon 13 here, it's got one more neutron, and 6 plus 7, yep, that's 13, right? And so this is the number of protons and neutrons in there, which is very similar to its atomic mass. For inter-level chemistry, you can think of them as the same. Like the atomic mass is the number of protons and neutrons. And then you can see like carbon 14 here has another neutron. The most common of these is carbon 12. Carbon 12 is pretty much what carbon is, and then you've got a small amount of 13 and 14. Most elements have a very common isotope. Like this is the most common of the 3 isotopes for carbon. But some of them will have like 2 or 3 that are fairly common, but not that common. So yeah, just be kind of careful. Also, yeah, isotope literally means same place. It's like the same place on the periodic table. I want to show you also real quick the simulation to help you kind of get a good understanding of how this works. So you can see with this that you can actually build some things on the periodic table, and it's pretty cool. It lets you like build these different elements, and then you can also see like, hey, if I change my neutrons, does that change my element? No, it's still helium, but I'm having different number of neutrons present for that helium. Okay. So this is a nice little way of just kind of playing around, seeing how this stuff kind of relates to these numbers that you might see in a periodic table. So if you have a periodic table open and you play around with this, you can kind of see how these things relate, and it's kind of neat if you ask me. I think that this is a really good learning tool. So I'm just going to make carbon, and then I think right now that would be carbon 12. So that's one of our isotopes. Should also probably get some electrons on there to balance out the charge. So this is a neutral carbon 12 atom. And you can kind of see like, oh, well, it's neutrally charged. It's got that mass of 12. If I add on another neutron, oh, wait, it's gone up to 13. So this is that carbon 13, and then carbon 14, which is an even rarer version of carbon. You can see that. If I add in another proton, it's no longer carbon, though. Carbon needs to have 6 protons. Carbon always has 6 protons. Elements always have one number of protons, essentially. And then also, yeah, you can kind of see how this relates to the symbols as well here. Kind of a neat thing to play around with to help you see how these numbers all work on the periodic table and how they like to display them, right? So there's that PhET simulation, which is a good way to help you kind of see the different isotopes. And the isotope should always be the same element, like carbon. And then also, yeah, this is pretty sweet. Oh man, I really like this for just demonstrating what isotopes are. So the interactive periodic table, it might, if you go straight to this, take you to the properties page. But if you click over to isotopes and then you click on something like carbon, it will show you all the different isotopes for carbon in this like weird drop down menu. And you can see like carbon 12 right there. Carbon 12 is, what does that say, 98.89 abundance. Almost all of carbon is carbon 12. Like carbon 13, yeah, it's about 1%. Everything else is so small they don't even show up on here. they're not very common or abundant. Hydrogen, you can see also it's got a ton of different isotopes, and then like the percent abundance down there, you can kind of see like, oh, like this has a small percent abundance here, and what's that percent abundance? Most of them are near zero because they're pretty rare. And then I believe that this should be pretty much all hydrogen 1, but having a hard time showing that. Let's look at oxygen. Oxygen should be mostly like oxygen 16, I believe. Yeah, it's like 99.7% oxygen 16. See, most of these isotopes are one version, and then you have some other versions that make it slightly higher or lower. Like you can see that, yes, this is most of oxygen, weighs this amount, but it's going to get a little bit of a heavier atomic average mass from these isotopes, though not very much because they don't contribute very much. They're very small portions. And yeah, I would highly encourage you to just kind of click around and play around with this thing and see the different isotopes and their relative abundance. As you can see, practically 100% of this is this one isotope, the sodium-23, which makes sense because that's kind of close to the mass that you see on the periodic table. So you've got all these different masses. They're coming together in different amounts or portions, like we saw with the heights analogy. And that's going to ultimately determine the percent that we see. Though most of the time, one thing is pretty much all of the sample. And so your average ends up coming close to that value. So just kind of keep that in mind with these types of problems, is that the average should be close to the most common or highest portion of your average calculation. Also, fun fact, the Earth has a certain ratio of isotopes because we got our isotopes from the same reactions on Earth. Like carbon 12s on Earth all came from similar reactions. But different planets might have slightly different ratios of isotopes. So iron might weigh something here. But if you go to like Mars, or if you go to like a different solar system, you go to like a different star and you weigh things there, iron might have a slightly different weight there because the isotopes there are slightly different. It's kind of cool. There's another way to think about these average calculations. That if you're kind of struggling with the math, this just shows it visually. So if we had like our problem earlier where we were talking about heights, like the 12, 13, 14, and 12 was 50%, 13 was 25, and 14 was 25. Instead of thinking about that as like heights of a plant, you can now think about that as like the actual weight of these different isotopes. And so you can think about like this is a histogram where you've got all these different heights, like the 12 and the 13 and the 14. And then you can make this as wide as the portion of the whole sample that we have. So we've got 50 and 12. We've got 25, 13, and the 25 and 14. And when you're averaging these out, you can think of it as you're taking the extra height here and moving it down there until they're all the same level. And that's basically what you've got here. Here you can see it's somewhere between 12 and 13. It should probably actually be more like right there, I believe. But you can think of an average as like taking the largest numbers and making them smaller, and taking the smallest numbers and making them bigger until they're the same height. And you can think about that as like cutting off some of this height, moving it over there until we get to the same height. And that's just a nice visual way of thinking about these problems. And the same thing could be done for like if you considered every single individual number and their height. But you can show this also with like the portion on the bottom there. So that's just a nice visual way of imagining what we're doing by looking at the different isotopes. In this case, this isn't height anymore. This is the mass of the isotope. So for doing mass of carbon isotopes. And then this final mass is the average. And that's just a nice way of thinking about it, if you ask me. Okay, let's do some calculations. Let's say that we're working with whole numbers at first just to make this easy. In reality, isotopes, they don't weigh whole numbers, but oftentimes with like introductory chemistry classes, they'll just tell you that it is a whole number just to make it easier. So if we're looking at doing this calculation, we have the average, which we're trying to calculate, and they've given us the amounts, the portions present. And so we literally just do this multiplication where we have the average is equal to the first mass times its portion, the second mass times its portion, the third mass times its portion. So you can see in this case we have, I've kind of reversed this, the 0.5 should be the second number, and the 12 should be the first if we're going by this formula. But if we do this, you can actually calculate that, and so you get like 6 plus 0.25 times 13. Yeah, I can do 0.5 times 12, but 13 times 0.25, that's 3.25. 3.25. And then we're adding to that the, what is that? 14 times 0.25. Nope. And that's 3.5. Okay, and we add those all up and we get the 12.75. And then this is gotta be AMU for the units for that number, because we're talking about atomic mass. So yeah, that's the main idea here, and I believe that that's the same number that I talked about earlier when I had my little table calculator. So if we have 12 times 0.5, add those out, you get that number. 13 times 0.25, you get that number. 14 times 0.25, you get that number. You sum them all up and you get the average. And so you can see that the average here does kind of match what we were talking about earlier. Unfortunately, things aren't that easy in the real world. Let's just practice, though, this concept, just doing it with the whole numbers right now. So if we want to find the average molar mass of this thing, this element here, we've got copper, I think. Yeah, Cu is copper. So we're going to have, let's say, the mass, let's just say it's 63. It's not actually. And then that's going to be times 0.70, because 70%, if you're trying to write it as a portion, you write it like this. And then we've got, what is that? 65 times its portion, which is 30. She write out like that. Remember, portions are out of 1, percents are out of 100, so you got to move that decimal place over 2 spots. So if we actually were to calculate that out, let's do that calculation. We've got 63 times 0.7, that's 44.1, plus 65 times 0.3, yep, 19.5. If we add those two numbers up together, you get an average of 63 point, what was that, 6? 6, yep, AMU. So that's our average for that compound. Now, oftentimes they'll give you the average and they'll ask you what portion you have of a certain element. So you might have something where they give you, actually, let me make one real quick and I'll show you. Okay, this is kind of what I'm talking about. And they typically show this form where you have the atomic mass, and then they may have told you the amount of the different isotopes, and they want you to tell you what portion there is. Um, it's kind of tricky because they're making you do some algebra where you're having to FOIL some numbers here. But if you think about this as zero point 0.7 and zero point 0.3, you should see how they're related. Like all the portions should add up to 1. So if you're only really working with 2 isotopes, they should add up to 1. So they've got the x and the 1 minus x here. You can think of that x in this situation is the 0.70. And so you can also think of 1 minus x. That's 1 minus 0.7, which is the same as the 0.3, right? And so this is 0.3 right here, which is the same as that number originally. So this is just rewritten. It's the same thing. It's just that we're using a little bit of algebra, and that allows you to solve for x no matter what. So in this situation, if you're trying to do this, you get 63x plus 65 minus 65x, right? You got that distributed. This was equal to the 63.7. And you can essentially just do a little bit of rearranging and you should be able to get this, right? So if we look at this, 63, what is that? 63 minus 65, so that's minus 2x plus 65. Yeah, it's kind of interesting, huh? So we've got our, what's that? Oh, wait, hold on. Yeah, we're gonna have the plus 65x, and then this was the 63.6. Sorry, I had a little brain fart there. Okay, so we have minus the 65. I got a little bit concerned because my math wasn't working right in my head. So we've got what is that? 63. So it's like 63.6 minus 65 is negative 1.4, and that's equal to the negative 2x. If you divide both sides by negative 2, then you get x is equal to 0.70. So you can do a little bit of, if you distribute and then do some algebra, you should be able to solve for the unknown portion as long as you know the molar masses. So it's pretty tricky there. You can think about this original formula. They're going to give you like a lot of information. They're either going to give you like the masses and then you have to figure out the portions, or they might give you portions and some of the masses, and then you have to find out the average mass. There's a number of things that you might have to do, but it's that algebra that can be a little bit tricky for people here. Um, you just gotta kind of check your understanding with your calculations, and you should be okay. So just be careful on those, okay? So in reality, it's typically not like 70 and 30% and stuff like that. Most of the time it's going to be where like carbon 12 is almost all of the sample. Like you have mostly one isotope and you've got a couple other portions here. So this basically you can think about the average for carbon 12 being equal to like 12 times 0.98 plus 13 times point what is that 0.15 plus the 14 times 0.005. And so in this calculation, if you do that math, you can I'm kind of cheating, but if we look at our uh, our math that we did earlier here on this little table, this is the 12 times 9.8 is 11.76. 13 times 0.015 is 0.195, and 14 times 0.005 is 0.07. And if you were to average that all out by just adding those numbers up, you get 12.025. So when we have mostly one isotope, the mass ends up being pretty much that. So this ends up being that 12.025 from those numbers that get added up when you do that. So this would be atomic mass units of carbon if these the protons and the neutrons weigh exactly 1 AMU, which they don't. They are slightly different. But sometimes in chemistry classes, they teach up to this point with just whole numbers. And so I wanted to kind of explain it from that perspective. Okay, time to get into the little bit more advanced chemistry version of this. Typically, you're told an AMU is a proton or a neutron. In reality, protons and neutrons weigh slightly more than what an AMU is defined as, because it's defined as 1/12 of a carbon 12 atom. It's kind of weird, and I'll do a whole video on the reasoning behind that. But long story short is that these numbers end up having some decimals on them. And if we go through one of these problems, this should show you how we actually get a molar mass with some actual probabilities that you would see in the real world, right? So carbon 12 is almost all of carbon. If you look at most carbon isotopes, it's nearly 100% carbon 12. 1% is carbon 13. Carbon 14 is so rare that you can say it's basically 0%. It's like 1 in a million are going to be carbon 14. They're pretty rare. So we typically don't even include them in these calculations. You could imagine it being like point like 0.0001 or whatever, but whatever this ends up contributing is going to be so small, it doesn't really change the calculation. So we don't really worry about things that are being multiplied by super small portions, because those isotopes don't really contribute to the actual mass very much. And this should be 889. I'm running out of space there a little bit. So we've got 12 times its probability. 12 times the 0.9889. And when we do that, we get 11.86. What was that? 8668. And then we're going to add to that the weight of carbon 13, because carbon 13 doesn't come out a nice even number. It comes out as 13.0035 for its mass, but it's only 1%, so we have to multiply by 0.0111, and that should give us how much it contributes, which is 0.144303. And we could keep on going, but these aren't going to be important for our final significant figures. If we add that to the 11.8668, we get the molar mass for carbon. So you can see the 12.011 that we typically see on periodic tables, right? If they gave us this, though, yeah, carbon is defined as exactly 12. So this is more like 12.00000. So it's not limited at 2. It looks like we're probably limited by the 3 sig figures in that percentage right there. So we could define this as 12.0, though it really is typically given as 12.01 most of the time. Okay, so that's our AMUs. I'm going to leave this as 12.1 AMUs just because you typically see it shown that way, and I'm going to add on a 0 of accuracy onto this because I can. The main takeaway on this is that it's okay for isotopes to have decimal points as their mass, and also keep in mind that it's almost always one isotope kind of dominating things. You do see this sometimes where there's 2 or 3 sometimes, but very rarely do you see more than like 2 or 3 common isotopes. If we think about that copper example, it is not exactly 70 and 30% as well. So let's get the actual percentages. So if we go to the interactive periodic table, yeah, you can see that in reality our numbers weren't quite right because of something with our calculation. But let's see. With the copper, it's going to be nearly 70% of this one, of the copper 63. You can see it's 69.17. And then this is 30.83. So 30.83. And 69.17. Okay. I think I might have flipped the numbers in their portions, so I just want to double check that yep, that portion is for 63, so 70% is for the 63. Okay, that's what I thought. I flipped the numbers. Okay, so this should be over there, and this should be over there. So you can say that that's like its percentage, and that's its percentage right there. And so we can say that the atomic mass for this compound should be its weight times its portion plus that its weight times its portion. So you can have that 64.93 AMU, and that's being multiplied by the 30, or not 30, because now it's writing this as a portion. 0.3083, and then add that to the other portion that's being contributed to the mass. That's a 6917. Okay. And so we can then do that math and solve for that. So if we get our 64.93 and we times that by 0.3083. What do we get? I'm just gonna go to there for now for our sig figs. We'll give a few extra just in case. In this case, we've got 62.92 times 0.6917. Okay, so that's our 43.5, what was that? 217. And if we sum those up together, what do we get? The 63.5, what was it? 5396. And if we round that to the sig figs, I'm going to actually use the sig figs for this. Say that there was four sig figs. It looks like all of our numbers that were given were 4 sig figs. So 63.54 AMU. So you could imagine that this could be significant, this difference now from what we got originally. Thank you for McLearning with me. I've got a few more offers that I'd like to let you know about, and remember, like and subscribe. For each video on YouTube, I am making an interactive version using HP5. These will be for sale on Podia, and if you click on the link in the video, you should be able to go directly to that product. I also have 2 demos I'm going to be linking so you can kind of see what these products look like. So I would recommend checking out those demos. I also offer one-on-one remote tutoring through Wyzant. Please use the links that I have linked below. That way I can get 100% of the hourly rate as opposed to 75. Each video also has a link for my Patreon, and you can join at the $3 level to get some resources I use for tutoring or to support the channel. And I also have a $5 raffle level, which you could either get some free online tutoring or 5 interactive lessons for free. You choose which ones. And then I also have my Teachers Pay Teachers, which has some old lessons that I made from when I used to be a teacher. I may be adding to that. Thank you for spending your time with me. I hope that you learned something.